bad. It is 5:20, so I guess we should go ahead and get started, even though we've only got two of you folks here. Do you have any questions before we get started? This is a time for you to ask questions about Chapter 17 homework, Chapter 18 homework as well. Anything
I don't
else?
have questions, but I will have to leave early to make it out to the lab tonight.
Okay, not a problem. And you can always do that. Let me know. And remember, I sometimes even after everybody signs out, sometimes I finish a little bit more work. So
Yeah,
if
I
you
know. So I'll have to watch that.
yeah, if you ever
Yeah.
do get to the end of a video or finish watching it, double check at the end. Just look, because sometimes I actually do another example or finish an example I was working on. So just nice to have that news out there on the interwebs.
Yes, it's nice to have that out there. Yeah, thank you.
No
Appreciate it.
problem. All right. Well, as I said, you feel free to just interrupt me if you have any questions. We are essentially finished to some extent with chapter 18. I want to reiterate what I had told everybody regarding chapter 18 and specifically the sections we cover. So, for instance, the kinetic theory of gases was when well, your textbook author actually derived from the ideal gas law and what we call basic kinetic theory and the ideas of what an ideal gas is. He was able to derive basically a expression for the average kinetic energy of the molecules or atoms of an ideal gas. Specifically, that's more of an ideal monatomic gas, but also specifically it applies in the right temperature ranges for any gases, because we find out in chapter 19 that there's actually certain temperature thresholds at which some of the different freedom arises for the atoms. And when I say freedom, I'm meaning degrees of freedom. So one way I've heard that I think is particularly good at describing degrees of freedom is the number of variable squared quantities that you have for energy. So, for instance, you guys remember that with a mass on a spring, which is how we pretend an atom is, it's basically an atom connected to another atom by sort of something like a spring connecting them. So, you know that has a 1 degree of freedom from the term 1/2 kx squared. But you also know that, when it extends the spring all the way to its farthest stretching point, the velocity is zero. But when the spring comes back and reaches its equilibrium point, the compression and therefore the spring potential energy is zero. But at that time, you have kinetic energy, which is yet another variable squared. That's 1/2 mv squared. So that's 2 degrees of freedom. Now, if you imagine that instead of it being a point like object, like an atom is, that it's, say, a pair of atoms that are connected to each other by a single spring, meaning a diatomic element like hydrogen, oxygen, nitrogen, something like that. That's actually just two identical atoms. You could also have just any diatomic molecule, which uses two different atoms as well. But the big thing is there that in addition to the center of mass moving left, right, or in, out, or up, down, which, each of those have a 1/2 K, or excuse me, a 1/2 mvx squared and a 1/2 mvy squared and a 1/2 mvz squared. So that's 3 degrees of freedom for the translational velocity of this dumbbell looking shape. It can go forward and backwards, which we might call the x-axis. It can go left and right, which we might call the y-axis. And it can go up and down, which we might call the z-axis. But then we also have a fourth degree of freedom because it can vibrate this way. Uh, but you can go further with further degrees of freedom by imagining the two atoms on the end of the spring rotating about this axis or rotating about this axis. There's two more degrees of freedom. So now we've gotten all the way up to 6 degrees of freedom. But it turns out, like we'll learn in chapter 19, that those other degrees of freedoms don't always just automatically kick in. So, for instance, you'll find that the degree of freedom associated with an atom or a molecule rotating this way or rotating this way evidently doesn't activate until it gets above a certain temperature. Okay. The other big thing that you got to learn from this, though, is that in chapter 18, what we derived was that the actual temperature is directly related in some sense to the average random kinetic energy of the molecules and atoms. But I want to rephrase that to say the temperature is directly related to the average random kinetic energy of translational motion of the atoms and molecules. In other words, it only considers the 3 degrees of freedom associated with the whole molecule, whatever its shape may be, moving left and right, or in and out, or up and down. Okay. So those three are the only ones that contribute to the idea of temperature. So if you look at something like water, water is a molecule that I often describe as a Mickey Mouse molecule. You can sort of picture it as Mickey Mouse being the head being the oxygen atom, and then two protruding ears, say, on the other sides like that, and those are the hydrogen atoms. This has the ability, of course, to rotate about this axis, dead through the center, but it also has the ability to rotate about this axis, and it also has the ability to rotate about this axis, and it also has the ability to do 1/2 kx squared vibrating about this bond and vibrating about this bond. So what you find is all those extra degrees of freedom are basically tranches that you can push energy into that go to doing things other than increasing the temperature of water. So there's an idea called the equipetition theorem, which basically says, hey, if you've got 5 different ways in which energy can be distributed, and it's a really big system, a statistically huge system, like Avogadro's number allows us, then it's extremely unlikely for any one of those 5 tranches to have more energy than any of the others. So we end up imagining that 1/5 of the energy goes to one way of distributing it, another fifth goes to the other, another fifth goes to the other, and until all 5 are done. So when you think about it that way, you think, okay, I'm adding temperature or I'm adding heat to the water, and only 3 of those degrees of freedom are going to increase the temperature. But if it has 6 degrees of freedom, that means only 1/2, 3 out of 6 of the degrees of freedom are contributing to the temperature at all. The other 3 degrees of freedom are just making the atoms, or in this case, the molecules, more agitated without increasing the temperature. And therefore, you might reach the conclusion correctly that water is a good insulator. And that's exactly what it is. The fact that it has a hard time changing temperature without an appreciable amount of energy is the hallmark of an insulator. So that's why, for instance, even though Great Britain has latitudes comparable to Canada and even northern parts of Canada, their climate is very much like maybe more like Washington State in terms of humidity and rain and stuff like that, but closer to Oregon and California for temperature. Even though, again, their latitude's much, much higher, but it's because they're literally an island. They're an island surrounded by water, and that water is an insulator, and therefore it's hard for the air temperature to get much colder or much hotter because the water acts as a retardant to that. So hopefully that makes some sense. As I was saying in chapter 18, we do cover kinetic theory of gases. That's where I came up with the 3/2 kT is equal to 1/2 v squared bar, where that is the square of the VRMS, what we call root mean square velocity. That derivation is something you should strive to be able to do, but it's certainly not something I would test you on. But your ability to do it helps you better understand exactly when it's valid and the purpose of it. And I promise you'll never forget it if you do. After that, it went into the ideal gas law and the molecular interpretation of temperature, which again is a continuous of that. And I did discuss that essentially. After that, it's the distribution of molecular speeds, which was the Maxwell distribution. That we definitely covered. In fact, I even assigned an extra credit problem. I think it's in our week 2 module. If it's not, just remind me and I'll put it there. I think yours was the class that I put it in first, and then I copied it to another class. But if I forgot that copying step, then that's why I'm saying it's best that you go ahead and let me know if it's not there. But that extra credit was basically, one, you needed to show that when I calculated the most probable temperature for a molecule to have by taking the first derivative of the Maxwell distribution and setting it equal to 0, that actually just showed it was an extrema. So it could have been a maxima, it could have been a minima, or it could have been a point of inflection. So the second test of that is the second derivative. So you now take a second derivative of that function and evaluate it specifically at the criteria that we discovered when we set the first derivative equal to zero. And if that result, that second derivative evaluated at that particular characteristic relationship, if that second derivative is negative, then we know that is a maxima. But if it's positive, we know that's a minima. So yeah, I think that's the way it goes. And of course, if it's a zero, it's a point of inflection. So that was the first part of the extra credit you were supposed to solve. The other part of the extra credit you were supposed to solve is I worked the problem. I think I made a careless arithmetic error or something in doing it, but I worked the problem of calculating the average velocity, not the root mean square velocity, but the average velocity by integrating f of v, the Maxwell Boltzmann, or excuse me, the Maxwell distribution times v dv. So I integrated f of v times v dv from 0 to infinity and then divided that by n, and that gave me the average speed. In doing so, I just grabbed a table of integrals for a definite integral and used that to get the result. My suggestion to you in the second part of this extra credit was you guys go ahead and try to do that same integral, but by using integration by parts instead of just looking up an integral table. Integration by parts is a very valuable thing, and everybody should know how to use it. So it's a great opportunity for you to work on that. Okay, so that's what we had done in the distribution of molecular speed section. I did in fact calculate a derivative of the the Maxwell's distribution. I did in fact do an integral with it, it times v, but not just it by itself. And I gave you a problem on it. And then the next section is section 18.3, which is on real gases and change of phase. We're going to talk about that in a second. There's also a section on vapor pressure and humidity. That's the section that I told you I'm not going to test on. It will be in your homework. It will be in your practice test, but it should not be in your actual test. The temperature decrease of boiling water with altitude. I love that. That's a great problem. And in fact, it was like the first problem that when I got to grad school at Chapel Hill, that was the first problem they tried to get us to do specifically in our training for our upcoming lab job, which was to teach labs throughout the semester. So it's an excellent derivation and an excellent result and that sort of stuff. But again, this is going to be a case where I'm not going to test you on it. You can have homework on it. You can have practice tests on it, but I'm not going to test you on it. Then the van der Waals equation of state, I'm taking a very minimalist approach to that. Specifically, I expect you to be able to solve what I'd call the plug and chug van der Waals equations problems. So those are ones where you're just giving the parameters. There's extra parameters in the van der Waals equation than there is in the ideal gas law. And it's a correction to the ideal gas law. So just a blatant application of those are certainly reasonable, even for the tests. Okay, the more advanced ones that take multiple steps and stuff like that, I'm gonna defer not to do those. That doesn't mean they're not valuable. They completely are, and they're completely important, especially when you take your steam table thermodynamics or whatever engineering thermodynamics you get. But like I said, I'm not going to test you on that more advanced application of van der Waals equations. And there's actually multiple versions in that subsection, so be prepared. The mean free path, I love it. I love the derivation. I actually worked out the derivation on my own for just sort of fun when I took the equivalent of this course. I definitely think it's something you should read. I definitely think it's problems that you should solve for homework. But again, I'm not going to put that on the test. And diffusion is just. I was muted. Now can you hear me? So I don't know what happened. We got bumped out. Can y'all hear me now? Okay. I don't know what you missed, but I was basically going over the sections. I'll real quickly just go over them again, just for what you missed. But what I said was the chapter on vapor pressure and humidity, not going to be tested. Definitely going to be on your homework and possibly practice test, but not tested. Temperature decrease of boiling water, definitely worthwhile to do your homework and practice test, but not going to be on your actual test. Van der Waals equation of state, will be on your test, but only in the easiest, what I'd call plug and chug form, where you're given the parameters and you don't have to do multiple steps in general. The mean free path, I love it. Super interesting, super cool, but we're not going to require that in the test, and we're not going to require the diffusion in the test too. But both of those, mean free path and diffusion, might pop up in your homework and your practice test. But again, I will not be giving you that. So let me go ahead and share my screen with you on the real gases stuff. So hold on for a second. I'm going to open this up. So now you're looking at a page from our online text. This is section 18.3, real gases and changes of phase. All of this reading is very valuable and gives you a very good understanding of the curves, for instance, in this case, pressure versus volume. They also have another one where it's pressure versus temperature. That, by the way, is also called a phase diagram because it gives you the ability to show when substances change phase. So definitely recommend you read this. It's a lot of technical aspects of facts and the way things behave. But I think one of the most important parts for you to see is this graph up here, where it has ostensibly graphs for the same substance at four different temperatures. A being the highest temperature, B being the second highest, C the third highest, and D being the coldest temperature. And what I want you to see is that the actual line, not the dash line, but the actual lines are real data. So you can imagine that he took the time to take an actual plot of actual data and made it this pretty graph that we have here with the pretty red lines. But he also showed with the dash lines what the ideal gas law predicts. So if you look at A, you see that that's the highest temperature one. And what you see is as we get to a lower and lower volume, or another way of looking at it, as you get to a higher and higher pressure, then the equation for the ideal gas, which is the dash line, differs from the reality of the data. So a couple reasons for you wanting to, for me wanting you to notice that is students sometimes have a hard time remembering exactly when is the ideal gas law most likely to be correct. Is it at low pressures? Because you might think that low pressure means the atoms aren't likely to stick to each other because they're moving so slowly or they're so far apart or something like that. But in fact, that's not right. Okay. In fact, what we see is as the pressure gets higher and higher, the curve deviates more. So as you can tell, it curved more away from that nice solid line to this, or excuse me, from that nice dash line to the solid line is the reality. So what you can see is for a given volume, if I go up, the real data is lower than the other data. So you expect the pressure to be a little lower uh, than an ideal gas law predicts, at least at high pressure. And you can really see that even better, for instance, with B, because if you look at graph B, you can see, let's take this line. I'm trying to choose a vertical line just to the left of that little point, lowercase c. So I'm shooting right up here, and you see this is the real data dot for that particular volume, but this is the actual pressure that the ideal gas law tells us. So we can see that the pressure is in fact going to be quite a bit smaller in that realm than the ideal gas law predicts. You can also look at it at a given pressure, and you can say, for instance, if I go across here at this particular pressure, reality is that it corresponds to this lower volume, but ideal gas law would suggest that at that pressure, it actually corresponds to this higher volume. So you can see also that the volume should be a little bit smaller than the ideal gas law says. So we expect the pressure to be a little bit smaller, and we expect the volume to be a little bit smaller as well. So that gives me a reason to talk more about the ideal gas law as compared to, for instance, van der Waals equation. So I'm going to leave this graph here, and I'm going to remind you to read all this stuff about liquefaction, which is also called condensation, about sublimation. That's the key thing that you're seeing here. Notice the curve difference for carbon dioxide, this lower graph, versus this upper graph where it goes and then turns back around over here. That's distinctly different behavior between water and carbon dioxide. What we do know about carbon dioxide is in everyday life, that's also called, anybody know what that's called? Like in the first aid community or EMSs, what would they call CO2? In addition to a greenhouse gas, obviously. You don't know. It's called liquid ice, or excuse me, dry ice. I don't know why I said liquid. Dry ice. Yeah, so that's what dry ice is. And it does something very specific. For instance, if you saw Real Genius, uh, Val Kilmer's, I think, first movie, anyways, 1980s, right? uh, you notice that they actually put a bunch of dry ice in their dorm and then it just disappeared and they didn't have to clean up any mess. Well, that's sublimation. It goes straight from the solid state to the gaseous state without actually becoming a liquid in between. You can see that very clearly. All of this line from the origin up to this triple point, that part of the line is sublimation as it is up here. Now we have a sublimation point for water, as you can see. All of these particular pressures and temperatures can allow water to sublimate. It can go from a solid straight to a liquid or straight to a vapor instead of to a liquid. But when you see that, you see it's at extreme conditions like atmospheres as low as 0.006. That's 0.006 of one atmosphere. So that's one atmosphere is 1.013 times 10 to the fifth Pascal. This is zero point zero zero 0.006 of that. So very low. Not only that, the temperature has to be 0.01 degrees Celsius. So you only get that for temperatures being lower and pressures being lower. So temperatures lower than 0.01 degrees Celsius and pressures lower than 0.006 atmospheres, that actually causes water to sublimate. Where when you look at the carbon dioxide one, you can see, well, I zoomed in on it too by accident. Let's zoom out a little bit. Okay, you can see that actually goes up to negative 56.6 degrees Celsius and up to 5.11 atmospheres. So anything basically in that area below 5.11 for all these temperatures up to 56.6, it can actually go there. But once you get to 56.6, if you're slightly higher than that temperature, then, or let's say you're slightly lower, then you can obviously go from solid to vapor. But if you're still in that one, but have a larger pressure than 5.11, you go from liquid, or excuse me, from solid to liquid, and then ultimately to vapor. So that's sort of what they're trying to explain with that. But now that I showed you that other graph, remember we concluded that the pressure is actually a little bit lower than it is for an ideal gas. In other words, a real gas has a little bit lower pressure than an ideal gas at high pressures, and it has a little bit lower volume at high pressures as well. So now I'm going to jump a few sections because I've already explained what's important out of here, and it's largely what you're reading, not what I'm saying, but make sure you read that. The next section was vapor pressure and humidity. I'm skipping that right now, which I'm sort of skipping it, period, but I'm mainly skipping it right now to go to van der Waals equations of state. And like I said, there's multiple ones here. So I told you, ideal gas law is PV equals nRT. Their first iteration of a change to that is this equation right here, which is not the full van der Waals equation. In fact, they have a name called, and it's called the Clausius equation of state. Whether you write it that way or this way doesn't really matter too terribly much. But the big thing is, I wanted you to see that they are, in fact, subtracting from the volume. Okay. And that B is an experimentally determined quantity that you can, in a sense, build a model on and then have a theoretical basis for what that B would be. But you can also just do experiments and figure out what that B would be. And if we give you the B, then you can just plug it in just and work just like an ideal gas law. So if you have all the variables but one, then you can certainly use it. So P, V, B, N, R, or well, N and T are the variables. So if you have all but one of those, you can solve for the other. And that's the sort of straightforward plug and chug problem I expect you to be able to do, even on the test. Here's another way. If you distribute that n by dividing both sides by n in the above equation, you end up getting this expression, which is really just the same thing as that other equation. But again, this is called the Clausius equation of state, and it predicts that for a given temperature T and volume V, the pressure will be greater than for an ideal gas. And if you want to go to the van der Waal equation, now they're climatizing us to the higher pressure that might actually be a result. In this case, you can think of it as, uh, I like to think of it as some of the volume has been taken away by the finite volume of the atoms. The atoms are really, really super small, but there's on the order of 10 to the 23rd of them. So that is a significant amount. And that's why you can think about this as being a minus. And you can sort of think about this as being a plus. And you can think about this as a result of the actual atoms tend to, or molecules, whatever you're working with, they tend to shy away from one another or repel one another uh, up close. And that's because basically the outer parts of an atom is essentially electrons, and those are negatively charged. And the adjacent atom also has an outer part that's mostly electrons that's negatively charged, and like charges repel. So that's going to do that. So, anyways, these allow us to better address those graphs that I was showing you earlier, and the critical point and all that good stuff. So that's the stuff you're supposed to do. As I told you, the mean free path is really cool, but this is totally not required of you for the test. The diffusion is cool too, but again, not needed for the test. I like to see your ability to read these sections and solve the simple problems they do give you. That's a whole learning skill in itself. So that's why I'm allowing that to go on. But that's all that's required for chapter 18. Now, what I did want to do, since I've worked all the other examples from the relevant sections, I wanted to show you how to work a particular problem regarding vapor pressure. So let's do this one right here, relative humidity. So I'm going to write this down on my iPad, and then I'll share my iPad and solve it with you. So let's do it this way. I'm going to change that from green and say, on a particular hot day.
I don't think you're showing that screen. If
Oh
you're
yeah, I got to copy it first and then I was going to share. But yeah, you're right. I didn't, but this time I actually knew. So on a particularly hot day, the temperature. So I'm just writing down this example completely. The temperature is 30. I'm going to call that 30.0 degrees Celsius, and the partial pressure, which you might not be familiar with, so I'm going to talk to you about that in a second, just in case you hadn't had chemistry before. The partial pressure of water vapor in the air is 0.030. I'm going to add another sig fig so I can have 3 ATM. And they want to know what is the relative humidity. So this is not a hard calculation. Uh, Again, it's more in the weeds. That's why I didn't really choose to show much about it, but it does give you some very valuable stuff to think about. So it's certainly worthwhile to have. So before we get started on that, I'll tell you that partial pressure is something that you learn about in chemistry. And also, if you ever take a scuba diving class, you'll learn about it as well. But let's imagine the air of our atmosphere was perfect and that it was exactly right to say 20% of it is oxygen and 80% of it is nitrogen. We know it's, not exactly 20 and 80, because there actually happens to be argon and water vapor and carbon dioxide and carbon monoxide and mercury and all sorts of stuff in our actual atmosphere. I don't know how much mercury is. I just assume it's there to some extent. I know there's some in the ocean. But the big thing is if we had an ideal atmosphere that was really made of 20% oxygen and 80% nitrogen, then if we were dealing with one atmosphere of pressure, remember that's another unit of pressure. It's the same as 1.01 times 10 to the fifth Pascal. If you had that situation, then the partial pressure of nitrogen would be 0.80 ATMs because you're literally multiplying the percent composition by the actual pressure. And the partial pressure of oxygen would be 0.20 atmospheres. Okay, so that's what partial pressure means. Now, in this case, we're going to use this formula. So our solution is, I'm getting ready to share the screen too. Don't worry too much. Okay, our solution is going to require the relative humidity formula, which I'm just going to write as relative hum, REL hum, and it's the partial pressure of water divided by the saturated vapor pressure. Oops. I'm going to share this in a second. Don't worry, I haven't forgot you. Evidently, I've forgotten how to write, though. And then we multiply that by 100%. So in other words, you just move the decimal two places to the right and put a percent symbol on it. I'm going to clean that up, and now I'm going to share the actual iPad screen with you guys. So let's stop the share, and let's start this other share, which is this one. It should be popping up for you any minute now. So this is the example that we were just reading. It says on a particularly hot day, or on a particular hot day, the temperature is 30 degrees Celsius and the partial pressure of water is in the air is 0.030 atmospheres. So they want to know what is the relative humidity. So the relative humidity for this particular example, which I'm just going to say RH, is actually equal to the partial pressure of water. In this case, it's 0.030 atmospheres. Again, that is a unit of pressure, don't forget. And then the saturated vapor pressure. So what we have to do is take that 30 degrees Celsius and we look at the table in your textbook, which I'm going to pull up right now. It actually happened to be right above that example, but on that same section of the page under vapor pressure, it's table 18.2. And from table 18.2, we get the saturated vapor pressure to be equal to, since we're at 30 degrees Celsius, it's 0.042. So 0.042 atmospheres is the saturated vapor pressure. What that means is at 30 degrees Celsius, if the partial pressure of water gets as high as 0.42 ATM or atmospheres, then or 0.042 atmospheres, then we will have rain basically. The water in the atmosphere will condense out by any minute little reaction. This is not unlike what you probably saw with supersaturation when you were in like elementary, middle school, earth science, and stuff like that, where you could take and let's say heat up the typical examples like tea. So you could take tea and you heat it up, boiling the actual bags of tea. And then while it's still boiling hot, you can add copious amounts of sugar to make sweet tea. And you do that. In fact, that's most of the way people make sweet tea. You stir it really good, and then the actual sugar has been completely absorbed by the liquid, and that was because it could handle that much sugar, specifically because it was such a high temperature. But now after you do that, you've got it all stirred, it's going to slowly come down to a lower and lower and lower and lower temperature just from being in an atmosphere that's not, approaching 100 degrees Celsius because you were boiling it before. As that happens, you could actually get down below the saturation vapor pressure, which, for instance, on let's say, a typical day, which would be 20 degrees Celsius. That's a pretty hot one, or 68 degrees is not too bad. But the vapor pressure there is 0.023. So in this case, what's going to happen is once you take that water or that tea that has sugar mixed in it and you bring it down to a lower temperature, then it'll have a whole new saturated pressure for sugar, not to be confused with the one for water, but for sugar. And all it takes is, like, you could take, this is the description they gave us in my earth science book in middle school, but basically you could take a single crystal of sugar and drop it in that sweetened tea, and it'll cause all of the sugar to precipitate out. Not all of it that you put in, but all that is above what it could actually handle for that given temperature. So once you brought it down from 100 degrees Celsius to maybe 20 degrees Celsius, because it's at 78 degrees or 68 degrees in your restaurant or whatever, and you just got it at room temperature, the amount of sugar that can be absorbed at that is a much lower value than, say, the 2 cups per gallon that you used for the sweetened tea when it was hot. Maybe it can say just half a cup. So if you actually did this experiment and really brought it up to these data values, and that those data values I gave you, if we imagine them as being absolutely correct, specifically that at 100 degrees it was able to take 2 cups per gallon, and then at 20 degrees Celsius it can only take a quarter cup per gallon. What you'd find out is, as soon as you drop that little crystal of sugar into the hot tea, that's now at 20, or excuse me, into the sweetened tea that's now at 20 degrees Celsius, basically 1.5 cups will precipitate out instantly. Okay. That's precipitation in terms of sugar being submerged or dissolved, if you will, in the liquid. That's exactly why we call rain precipitation, because it does the same thing. It has a specific amount that it can handle. But now that we've done all of that, I can go ahead and use this result. I do see that the saturated vapor pressure for water at 30 degrees Celsius is in fact 0.042 ATM. So I'm going to take the 030 and I'm going to divide it by 0.042 ATMs, like that. And then I'm going to multiply that answer times 100% just to make it into a decimal. When I do this, I get 0.3 divided by excuse me, I messed up again. 0.03 divided by 0.042. And that gives me 71.4% is the relative humidity. Now, your book does another example that is really just a conceptual example, but it's very good and explains to you, for instance, why your skin is dry in in the winters, why you often shock yourself when you go to grab a doorknob in the winter, all that sort of stuff. And that's basically handled in the next example, which I'll read to you now. Actually, let's go ahead and I'll show you this one because it's helpful anyways. Now I'm going to share that same screen again from the textbook, that is. So if you look down here at this example, it says conceptual example 18.7. Why does the air inside heating buildings seem very dry on a cold winter day? So what he's doing is he's saying, okay, suppose the relative humidity outside on a negative 10 degrees Celsius day is 50%. So what they're doing is they're saying, okay, we've got relative humidity. I'm going to write this down here and recap it when I pull the iPad back up. So I'm writing the information down right now. We're saying outside temp is equal to negative 10.0 degrees Celsius, and the relative humidity is equal to 50%. And it says, what can we basically figure out about why the air feels dry in there? In this particular example, they're then going to use that and calculate the relative humidity inside of the room. Okay, so next we're going to say inside temp is equal to, yeah, chose 20.0 degrees Celsius. And what we want to know is what is the RH inside. Okay, so let's go ahead and attack that. Now that we've had this reading, you can actually read the solution as well yourself, but I wanted to explain it to you because it's not, it's not completely obvious. It does take a little bit of work. So now I'm going to go back, share my iPad screen again, and you can see I've already got the data written down for the conceptual example 18.7. Oops. Okay. So the outside temperature is this, and they gave us the relative humidity, which means, it's about 50-50 chance for it to rain. So that's still kind of a fairly humid day, even though it's cold outside. But they told us it's 50%. So that means relative humidity, which is equal to the partial pressure of H2O divided by the sat pressure of H2O times 100%. So from that, we can say 0.5 is equal to the partial pressure of H2O. But since we were told that the temperature is negative 10 degrees outside, I can look back at table 18.2 again and find out what the saturation pressure is. And the saturation pressure at negative 10 degrees Celsius is 2.6 times 10 to the negative third atmospheres. And notice I wrote the percent as 0.500 instead of 50.0. So this version should not include the one times 100% on the end. I've already basically made that happen. So now with that, I can use it to determine what the partial pressure of H2O is, basically just by multiplying 0.5 times 2.6. So that'd be 1.3 times 10 to the negative 3 atmospheres. So that's the partial pressure of oxygen. Okay. And remember that essentially means since the atmosphere is one atmosphere, or since the pressure is usually one atmosphere of pressure, and the partial pressure of oxygen is 1.3 times 10 to the negative third, that's 0.0013. That's literally the percentage of the air that's oxygen. That's water. Now I can use that to calculate the relative humidity inside. And that relative humidity is going to use the same partial pressure, which is 1.3 times 10 to the negative third atmospheres divided by, now I'm going to take the the saturated vapor pressure for 20 degrees Celsius, which according to table 18.2 is 0.023. I'm going to put a zero on the end of that again, just so I can get 3 sig figs. But I have no idea if the zero is actually accurate. Well, actually, I should have just left it because the 1.3 was only 2 sig figs. So anyways, we'll just do that. So I'm going to take 1.3 times 10 to the negative 3, and I'm going to divide that point by 0.023. And then I see that that's 5.7%. It's actually 5.652. but the 5 and the 2 at the end are not sig figs. So you can see, even though it was 50% humidity outside, when you came inside, that same air that's being pulled inside now has a relative humidity of only 5.7%. But even if it was so horrible outside that we were absolutely at 100% saturation, meaning it was definitely getting ready to rain on this freezing cold day, even if it was that case, then what we'd see is specifically the partial pressure would be exactly equal to the 2.6 times 10 to the negative 3. So relative humidity with 100% outside. This relative humidity would be 2.6 times 10 to the negative third atmospheres. And then I'm going to divide that by the saturation pressure, which is 0.023 atmospheres. Again, that's just corresponding to a given temperature. And I am moving the decimal on my plate on my own. So there's a step that I'm not really showing, and that's the times 100% in these last two equations I've written. So it's not going to be written in this last one either. So I just take 2.6 times 10 to the negative 3, and I divide it by 0.023, and that gives me 11.30%. So even if it was completely dank feeling outside because of 100% humidity, it's still only going to come up to about 11% humidity in that room. So that's the reason that we feel basically dry in the winter. And that's also because there's, when water's in there, water is a polar molecule, and it has a definite end that looks sort of negative, and it has a definite end that looks sort of positive. And those different ends being polarized, they attract things that have the opposite sign. So the positive end is going to attract any negative ions, and the negative end is going to attract any positive ions that might be in the air. So you scuffing your feet on the carpet really releases charged particles to some extent, and in fact makes you net charged. But if the air is really, really saturated with water, or even just has a little bit in it, a pretty, on the order of 20% or so, once it starts getting to 20, 30% or something like that, then that water can essentially rather quickly take out the ions from the air, and therefore from your body as well. So you wouldn't actually get shocked when you walk up to a doorknob that is basically grounded. Because if it's dry, then you still have that net charge on you because the atmosphere wasn't able to absorb it, because there just wasn't enough water available in the atmosphere to attract the extra ions. So now you go to touch the doorknob with a hand that, let's assume that the rubber of your shoes had a greater electron affinity to than the carpet atoms did, or the carpet molecules did, so that I'm now a net negative charge. So I have all these electrons on me. My fingers are negatively charged, and I go to grab a doorknob. The doorknob's made of metal, of course, and being a metal, the negative charges of the atoms or molecules in the doorknob run away from my side of the doorknob, and then all of a sudden my side of the doorknob looks a little positive, and the electrons that are extra on my hand will jump towards the positive charged looking. Again, it's not necessarily charged, it's probably just polarized, but the charged looking doorknob is attractive to the electrons on my hand, and they will in fact jump, and you can literally see something that looks like a little lightning strike jumping from your fingertips to the doorknob. And that's what it is. I mean, it's literally a lightning strike, because lightning is just the ionization of air, providing a path for charges to run down or up to the cloud to basically make the voltage difference between the cloud and ground about zero. Okay. Hopefully that was somewhat helpful to you. Hopefully I didn't use too much gobbledygook or jargon or whatever you will. But that also brings me to another issue. And yeah, we got plenty of time. The other issue,
Professor, one question for you.
go ahead. And then
Looks like a couple questions.
go ahead, Matthew.
Um, can you explain the decision to use atmospheres rather than pull from the table 18.2, using the pascals?
Yeah, there really isn't a preferred method. I think there should be in some sense a preferred method just because the number you work with when you're dealing with atmospheres is one. You know, if it gets really bad, it might be high pressure wise, it might be 1.04. You know, or if it gets really low pressure like in a hurricane, it might be 0.992 or something like that. Okay, so the numbers are just better to work with. So a lot of times it's nicer in that sense to work with atmospheres. But that's really the only reason. There's an easy comparison to them. I mean, you can convert them back and forth. In fact, at the bottom of the table, they even give you some data. For instance, they tell you 1 bar is actually 10 to the fifth Pascal. So when I say the atmospheric pressure is 1.013 times 10 to the fifth Pascal, I could also say that the atmospheric pressure is 1.013 bar, which is just like the atmosphere. So that'd be pretty nice. I could also use the torr, and the torr is defined such that 1 torr is the same thing as 1 millimeter of mercury, which is another uh, pressure value or pressure unit we use, but they correspond to 133 Pascal. So yeah, there's just no good reason other than we like those units. So either one will work.
Got it. Got it.
Was there
Thank you.
another
I
question you
mean,
had? I thought I had two.
I have to go though.
Oh, okay.
So I
No
can drive
problem.
back to school. Okay.
If
All
you
right. Thank
send
you.
me, no problem. If you send me pictures of the problems you had, I can send you a solution or make one or something. So just go ahead
Okay.
later on, send it, text me with it.
Okay. Sounds
Okay.
good.
All right.
Thank
See
you.
ya.
All right.
Thanks, Matthew. Did you get both your questions asked, or did you decide you only had one, or did I mishear you?
No, I just had the one. I was
Okay,
speaking
that's
for
cool.
Jennifer as well. Thank you.
Good deal. Yeah, there's no quote unquote right or wrong. I would, since I didn't do this with you guys earlier, I probably should go ahead and do this. I'm going to tell you, your book uses capitals for these, so I'll write it as well. So PV equals nRT is our ideal gas law. Your book also took the time to show you that you can alternatively write it as capital N times K times T, where this capital N, or excuse me, where this K is the Boltzmann constant, which is equal to the gas constant divided by Avogadro's number, and that equals 1.3807 times 10 to the negative 23rd joules per Kelvin. So that's one way. But the other part that I'm stressing here is the R value that we use in the version to the left. That's 8.314 joules per mole Kelvin, but that's also equal to 0.0821. And in that case, it's liters times atmospheres divided by moles times Kelvin. And then there's another one that pretty much we only use this in chemistry. We use the 0.0821 and the 1.99. Those are the two ones I remember using in chemistry most often. Occasionally I would use 8.314, but most of the time it was those. This one is 1.99. And this one's kind of weird in that its unit is calorie per mole Kelvin. Okay, that's a regular calorie, not a kilocalorie. So even if my C looks a little bigger than the A, I mean them to be the same size. So the rules associated with this ideal gas law is P must be the absolute pressure. And I should let you know that P atmosphere or P total, or let's call it P absolute. Ooh, let's try to learn how to spell when I go to write that too. That'd be cool. So absolute, I'm going to go ahead and write it out as absolute. Oh, good Lord, there's a lot of stuff to subtract here. Okay. Absolute pressure is equal to gauge pressure plus 1.00 atmosphere R the current atmospheric pressure. Okay. So that's how you get that. I noticed that some students are having problems with this. They didn't understand about gauge pressure and that sort of thing. So I wanted to point that out. Another thing is that temperature has to be measured in Kelvin. And remember, Kelvin is just the unit. It's not Kelvin. It's not degrees Kelvin. It's just Kelvin. Okay, so that's something that's critical. And also, the N is equal to the number of moles of the gas. And you can find it by taking the mass of the gas and dividing it by the molecular weight of the gas. Okay. The capital N is actually the total number of molecules. Okay. So that's what the capital N corresponds to. I've told you about the temperature, and I should say when you're using this result, then the pressure units should be pascals or newtons per square meter. The volume should be in cubic meters, and everything else is straightforward. In the second case, you can tell here that the units of the pressure obviously have to be in ATMs, and the units of the volume obviously has to be equal to the liter. And I should remind you that 1 milliliter is equal to 1/1000th of a liter, but it also equals 1 cubic centimeter. And then I'll also say that 1 kiloliter is actually equal to 1 cubic meter. So that should help you as well. Let me see. So I got that. I got the volume, got the pressure. Temperature has to be in Kelvin, so we don't need to restate that. And then this version here, this one actually requires us to use for the unit of pressure. It actually has to be what we call dynes per square centimeter. And that's a really, really complicated unit that ultimately reduces from F equals MA, basically reduces to grams per centimeter second squared. Yes, it would, yeah, so it should be that because a gram times a centimeter over a second squared is actually a gram, 1 gram centimeter per second squared is 1 dyne. Okay. But when I take a dyne and divide it by square centimeters, that cancels out the top one and leaves a single centimeter at the bottom. So that's what that is. It also expects you to have a volume in cubic centimeters. And everything else is the same. So in order to actually use this ideal gas law, you have to know those facts or you're sort of, up the creek without a paddle. All right. Now, we've done basically everything that we need to do for chapter 18. There's plenty of examples you can see in the book. There's plenty of examples you can see on my YouTube channel. I would probably say if I'm looking in chapter 18 for something on van der Waals equation, just to give you an idea how to do things, I would go to the problems from chapter 18 and specifically go into the section on van der Waals. And that's section 18.6. And actually, it looks like all of the problems in the book from this section are level 2 and level 3 problems. So they're pretty hard. But one example, for instance, it says, in the van der Waals equation of state, the constant B represents the amount of unavailable volume per mole occupied by the molecules themselves. Thus, V is replaced by V minus NB, where N is the number of moles. For oxygen, B is about 3.2 times 10 to the negative fifth cubic meters per mole. And they want you to use that to estimate the oxygen, the diameter of the oxygen molecule. What you're doing there, and you can work it from here. That is an odd problem. So the answer is in the back of the book. But basically, what you're going to do is you say, okay, well, B is supposed to be the volume of a mole of oxygen atoms. So you can basically say, well, the oxygen atom has a volume of 4/3 pi r cubed, where r is the diameter, or excuse me, r is the radius of the molecule. So that's the formula for a single molecule. But if you have, for instance, or for a single oxygen atom, if you had, for instance, N molecules, which is a mole, N number of moles, then you just multiply that volume times N. And in this case, that volume times N turns out to be 3.2 times 10 to the negative fifth cubic meters. So if you divide that by the number of molecules in it, which in this case would just be the per N, then you'd get the volume per oxygen molecule, and then you could set that equal to 4/3 pi r square or pi r cubed, and solve for r, and then double it to get your diameter. Okay, so hopefully that works. For oxygen, B is about 3.5. Yep. Yeah, that looks about right. Cubic meters per mole. So, okay, yeah, good deal. So hopefully that helped. If you have any questions on this, like I said, that's actually more complicated than I really want you to do on the test anyways. Whereas 42 looks like it might be a little bit easier because they give you the A and the B. So I would say 42 is a better representation, although 41 is a good problem to work. The 43 is actually a level 3 problem, which is supposed to be kind of complicated. So I would not say that's a fair example of what you expect. Now, with all that said, we've done basically all the good stuff that we're going to do with chapter 18. I'd like to get started with chapter 19, which is where we're going now. So I'm going to share my screen again. We only got like 17 minutes left, but that's okay. So I'm now going to go to chapter 19, which is on the first law of thermodynamics. We can see right down here, heat and the first law of thermodynamics. So this is the chapter, Heat and the First Law of Thermodynamics, chapter 19. As always, it starts with a chapter opening question that, as I've told you before, you should definitely make an answer before you actually find out what the real answer is. That way you can sort of do the scientific method in actually learning. So you're actually making an approximation of what you think is the right answer. Then you're going to learn from, usually it would be experiment and actual science, but in this case, it's going to be from reading your book. You'll find out what the real answer is, and then you can either pat yourself on the back for getting it right, or you can say, okay, well, what did I miss, and reassess from there. So definitely do that. This chapter, of course, has the first sections on heat and energy transfer. Specifically speaking, heat is the energy transferred from one object to another as a result in non-equilibrium, non-thermodynamic equilibrium. And non-thermodynamic equilibrium, meaning not being in equilibrium thermodynamically, just means two objects are contacting or interacting with each other in such a way that the two objects do not have the same temperature. So they might be touching each other, in which case the vehicle by which the heat transfer is going is what we call conduction, or it could be convection, or it could be radiation. But the more important thing is the heat is leaving the hot body and going to the cold body. That turns out to be how heat works. And in fact, the fact that heat leaves a warm body, a body of higher temperature, to go into a body that's touching it that has a lower temperature, that is the very statement of the second law, or one of the many statements of the second law of thermodynamics, whereas the first law of thermodynamics is just a conservation of energy statement. 19.2 talks about the internal energy. And what we mean by that is the total energy in a particular system, which might be a gas, for instance, like we were covering in the previous chapters, or it might be a chunk of matter. But the main thing is all of those atoms and molecules are vibrating and moving and stuff like that. So they have transverse or translational speed, excuse me, and they have vibrational speed and all those degrees of freedom we talked about. If you add up all those energies, which include, for instance, the electrostatic energy associated with the attraction between the atom's nucleus and the atom's electrons, as well as electro forces associated between one atom and another, or between one molecule and another, all of those have energies associated with them. And if you sum up all those energies, that would be what we call the internal energy of the sample. Specific heat, we specifically apply as sort of what I'd call a measure of the thermal capacity of a substance. More specifically, it really is how much heat does it take to raise an object's temperature by, let's say, 1 Celsius degree, if its mass is 1 gram, for instance. Okay, that is basically a statement of how hard it is to raise the temperature of something. So if that number turns out to be big, that means that it's a good insulator, and therefore it takes a lot of heat to make it change temperature. If that number is really small, it doesn't take as much. So for instance, water in units of calories, water has a specific heat of 1.00 calories per gram Celsius degree. So what that means is literally it takes the very definition of 1 calorie. It takes 1 calorie of heat to raise 1 gram of water 1 degree Celsius. And they even defined it very specifically. I want to say it's like from 15.5 to 16.5 degrees Celsius. The book tells you, but I think that's what it is off the top of my head. Uh, so however much energy that takes to raise 1 gram of water from 15.5 degrees Celsius to 16.5 degrees Celsius, again, assuming that I was right about those numbers, that would be the specific heat, and it's listed as 1.00 calories per gram Celsius degree. Okay, so that's what specific heat is. Calorimetry is basically our way of tracking calories in a physical problem where two objects or more objects are put in thermal contact with one another, and we wait until they reach equilibrium, and we try to calculate, for instance, what the final temperature is in equilibrium. So we're going to learn how to do that. That's very much a chemistry problem that you've done in the past. Latent heat, that's the extra amount of heat that you have to apply to a solid, say, to break the bonds that make up the lattice of the solid. And that would be the heat of fusion. Fusion specifically is supposed to be going the other way. So the heat of fusion would be the amount of heat that you'd have to take out, for instance, to allow it to go from liquid to a solid. Okay. But there's also latent heat of vaporization, in which case that's the one that finally frees the individual liquid molecules and atoms, which are relatively close to a particular atom at any particular time. And for a, atomically long period of time, which might be on the order of a couple microseconds, it spends its time around that particular molecule. Okay. So, because of that, those adjacent molecules have a pretty strong force holding them close together, such that they're almost like rolling on top of each other as opposed to being separate like this. When you actually get to the gaseous state, they're separated by a huge amount. So in order to break those little bonds between the individual molecules, you have to add a certain amount of heat that we call the latent heat. In this case, it's the latent heat of vaporization, and it actually is how much heat you have to add to it to make it go from a liquid to a gas. Okay. Then we go over the first law of thermodynamics, which is surprisingly easy. It basically says that delta U, we're using U, or sometimes we'll use E. Actually, I think your book might be using delta E. Yeah, it is using delta E. Sorry about that. Uh, we use delta E, the change in internal energy is equal to Q plus W. And you probably seen an equivalent version in your chemistry class, and in their class they use Q minus W. And that's an important distinction between the physics world and the chemistry world, specifically because we were looking at how much work is being done by the system, and chemists care more about how much energy is put into the system as opposed to how much energy the system can put out. So they treat work as negative when it's actually done on the substance, whereas we treat it as a positive. So that's why we differ in sign Q minus W versus Q plus W. Q is the heat added. Notice they don't put a delta in front of it. And W is the heat added to the system as well. But Q is normally given a form like MC delta T. So you'd multiply the mass times C, the specific heat, times the change in temperature. That would give you the whole heat added. And the work would be like the integral of PdV. So you could take the integral of pressure over a differential volume for going from one volume to another, and that would be the work done. So delta E, the change in internal energy, is equal to Q plus W is a typical version. Beyond that, let's look back at the table of contents again. Or actually, yeah. So after the first law of thermodynamics, which I told you was there, we're then going to go into a comprehensive study of the thermodynamic processes. So there's processes that are adiabatic. That means a process in which no heat is transferred into or out of the system. There is an isobaric process. That means at constant pressure. There's an isovolumetric. That means at constant volume. There's an isochoric, which I think also means isovolumetric. All sorts of stuff like that. There's reversible processes, and those are basically represented as two equilibrium state infinitesimally close to each other, so that you could literally give just a slight infinitesimal amount of work put into the system could cause you to go from one state of equilibrium to another state with no gap in between. Like we're pretending like it's this discontinuous event is actually continuous. And because it's only differentially away, it can equally easily be pushed back to that original state. And that's why they use the phrase reversible. Okay. So those are some of the processes we'll use, and we'll use them very detailed. Like we'll rewrite the first law of thermodynamics for an isochoric system. We'll write the first law of thermodynamics for an isobaric process. We'll do it for an adiabatic process, which hopefully you've recognized from what I said. Delta E equals Q plus W. If it's adiabatic, and I told you no heat is added or taken away from the system, then you probably suspect the new version of the first law of thermodynamics in an adiabatic process is delta E is just equal to the work done on the system, as opposed to Q plus W. It's just plain W because the Q is zero. So we'll do that. Then we'll talk about something kind of neat. So we already studied specific heat by the time we get to section 19.8. But what we find out is if we're dealing with gases, specific heat is really rapidly different from one state to the other of a given gas, and from one gas to another gas. So they're not really behaving in some uniformed way like we're used to with ideal gases. But if we instead talk about the specific heat, not per unit mass, but per mole, then it turns out we get some very regular results. In other words, gases have a very characteristic behavior with regards to specific heat, if that specific heat is in calories per mole Kelvin or calories per mole Celsius degree. So that's why we do molar specific heat. And then in so doing, we learn all these fundamental equations that relate internal energy to work and to heat and all that good stuff. They talk about an adiabatic expansion of a gas, and then finally we finish off with the three versions of heat transfer. Conduction being when two objects are physically contacting one another. Therefore, heat can flow from the hotter body to the colder body. That would be conduction. Convection, that's well, if you have a air fryer, or if you've been to 7-Eleven and see how quickly they can cook pizzas now, they're using what we call convection ovens. And basically, you use an intermediate substance in convection that can carry heat from a hot spot to a colder spot, and then fall back down after releasing its heat, fall back down, be reheated and reprocessed again. So that's what the convection aspect is. I like to use just the idea of a hot probe at the bottom of your coffee pot. So there's a hot probe at the bottom of your coffee maker. When you put the water in there, that hot probe slowly brings that water to a boil. The water then becoming steam floats up and more or less just condenses on the colder plastic lid. That colder plastic lid allows that water to fall off and land in the little container where the coffee is, and specifically where a filter is. And then that coffee percolates, literally percolates through the coffee, picking up some of the molecules of the coffee that make it a color other than clear like water is, and you get coffee out. So that process of heating the water up, actually delivering heat ultimately to the air above it, is a convective process as opposed to a conductive process. The water touching the hot probe is conduction. Okay, it's the circulation that makes it the convection part. And then finally, radiation is what we discovered when we did an experiment to locate the what they call the luminiferous ether. So we knew that all waves we've seen in the universe went through material, like we'd seen ocean waves and we'd seen earthquakes and sound waves. All of those are carried through material, and therefore we thought that maybe waves can only exist in material media. So we hypothesized the existence of an ether that was all over the universe, and that allowed us to imagine how the heat, which we later, thanks to Maxwell, discovered was in fact electromagnetic waves coming from our sun through space and then hitting our atmosphere. That seemed perfectly normal to them because it was filled with ether between us and the sun. But when we did the Michelson-Morley experiment, we discovered a null result, which basically said that no matter which angle you turn the spectrum or the device for measuring the speed of light, you got the same result, as if either the ether was being quite the trickster or there is no ether. So, in fact, a guy by the name of Lorentz made up an equation or a set of equations that was able to explain the magic trick that the ether was doing. And it seemed, in fact, if you look at those equations, it seemed like matter moving parallel to the direction of the motion of the ether actually compresses the material along that axis that's parallel to its motion. So that was a remarkable thing, and the equations worked out perfectly, but it was all in an attempt to save the idea of the ether. Around the same time, but shortly thereafter, Einstein hypothesized his special theory of relativity, which basically said the speed of light is a constant, independent of the motion of the source and the motion of the observer. And then part two said that the laws of physics are the same for all inertial observers. And from that, he was able to get the exact same equations that Lorentz got just by examining light in a very special way, using these thought experiments that were called Gedanken. So the tale of all that is that radiation does not need a material to go through. It's just carried by electromagnetic radiation. Specifically, parts of the electromagnetic spectrum are gamma rays, X-rays, ultraviolet, visible, and then in this way it goes VIB-GIOR instead of Roy G. Biv. But then after the VIB-GIOR, which is the visible spectrum, which is very, very narrow in the giant thing, after that is the infrared, and then after that is the microwaves. So my mnemonic I use is great excess undermines various industries' Marxism rules. So it goes visible, industry is infrared, Marxism is microwave, and the last R is radio waves, or excuse me, the last one is G. Sorry about that. So great excess. No, it was R. It was radio. I was had it backwards in my head, but you can look at that in chapter 31, I believe, if you need to. But that's what radiation is. It's the propagation of carrying energy, not necessarily matter, but energy from point A to point B via waves, and it does not need any material. It can do it right through a vacuum. So I've got us started on most of the reading, at least of chapter 19. Next time I will just be working problems straight from 19, but I'll also give you time to ask questions. So let me know if I can do anything for you. That's it. Feel free. Actually, do chat me your first and last name so I'll know you were here. But you're free to go. Thanks, Matthew. I appreciate you
Yeah,
coming.
Professor, I do have one question
Yes.
just about the schedule. Well, actually, I have two quick questions. One is about the schedule for the test.
Right.
Is that going to be on the 3rd of February? Okay.
No, I forgot to tell you all that too. Yeah, I'm glad you mentioned it. No, I'm moving at least this first test, but I'm probably going to move all of them, but maybe the last two exactly 1 week back.
Okay.
And
Yeah,
I've
great.
already moved the homeworks to some extent, so that hopefully that helped you. But yeah, the first online test, which was supposed to be this coming Sunday, it was supposed to be due. It's not going to be due till the following Sunday, and I'll probably make it available this week, if not the very beginning of next week.
Okay, great. Yeah, I think you saw my email. I'm heading out of town
Yeah,
for the week, so I won't see you next Tuesday, but I'll probably be able to attend this coming Thursday.
no problem.
Um, and then secondly, quick question on it was chapter 18, the Galileo question, Galileo's last breath question. I don't know if you remember that one.
I don't
And
remember that one. Was it something about the number of atoms in his breath or something like that?
yeah, yeah, and I was able to solve it, but the you had to assume temperature of 25, like an ambient atmospheric temperature of 25
Hmm.
degrees Celsius. Is that standard? I didn't know that that was an assumption that we were going to make. I just Googled
Yeah.
it, to be honest, and then came up with the right answer.
Yeah, it's 25. I wouldn't say is necessarily the best one. I would have probably leaned towards 20. That's what
Okay.
we call room temperature. It's like 68 Fahrenheit. But the complicating factor is we have this definition of standard temperature and pressure, STP, and that actually means a temperature of 0 degrees Celsius and 1 atmosphere. So at least it's better than the zero that we
Yeah.
normally. But yeah, you could have argued 20 degrees, 25 degrees. And in that type of situation, what you do is you're trying to just get the order of magnitude. So if your answer was 9 times 10 to the 24th, and the book's answer was 1 times 10 to the 24th, you would still be right because it wouldn't have an answer that close to it, like if it was
Okay.
multiple choice.
Yeah. All right.
Does
Yeah.
that make
Got it.
sense?
Yeah. Yeah.
All right.
All
Did
right.
you get your
Thanks.
lab stuff fixed? Are you able to make lab and stuff now?
Yes, I'm looking good for now. We're going to take it week by week, but yeah, it looks good for now.
Okay,
I was able to sort out a makeup with Dr. Johnson,
cool.
I think the following week after I get back. So yeah, I'm all set.
Okay, good deal. I was making sure I hadn't held you back again.
Yeah, no, we're actually I am going to run out. I'm gonna head out now, and I should be able to make it. So I'll see
Cool.
you next time. All right.
All right. See you, Matt.
Yeah.
Appreciate
Yeah.
it.
Thanks a lot. Bye.
Have a good one.